My name is Sarah Wyllie, and also here is my research partner, Bruce Zheng, and we're presenting Multiclass Classification for Network Intrusion Detection in Drones, a project mentored by Professor Ismail Abumuhfouz. Drones are flown via Wi-Fi network, in which the controller sends instructions to the drone. They are often used to provide Wi-Fi service in disaster-stricken areas and may handle sensitive military or health data. On the left is an example of a drone control network in which the user sends information to the drone, and on the right is an example of a drone providing a service to the users. In 2011, an American military drone was hacked. Hacks occur when an intruder sends malicious data to the drone. So we seek to stop this using an artificial intelligence, or AI, which can recognize if any data being sent to the drone is malicious. ANIDS is an anomaly detection system which uses an AI to detect unusual or suspicious behavior. We're using this not only to see if an attack occurred, but also to see specifically which attack occurred. AIs are trained from datasets, and we're using CIC IDS 2017, which is essentially organized like a spreadsheet. The rows are called records and the columns features. The final column, or label, determines what type of attack each record is. With this data, we alter it to reduce the chance our AI will become algorithmically biased. We begin with feature selection, which ensures the magnitudes of the data in each column is the same, and no features are overpowering the model. Train or teach the AI using k-fold cross-validation, which ensures the AI learns the data well without bias by training and testing the AI repeatedly. We then gather confusion matrices as our results, which you will see later. We tested 3 AI algorithms, each of which are computationally inexpensive and may run easily on board a computer on the drone, such as the Raspberry Pi. The 3 algorithms are random forest, stochastic gradient boosting, and k-means clustering. The first algorithm is the random forest with bagging or bootstrap aggregating. First, bootstrap datasets are created by randomly selecting records from the dataset. The same records may be in multiple bootstrap sets since the records are selected with replacement. Then, a decision tree, a simpler AI, is trained on each bootstrap dataset. Finally, the AI is evaluated by running the unseen data through each decision tree, which votes on what attack it thinks the data represents. The attack with the most votes is the prediction given by the random forest. And now, let my partner Bruce talk about the other 2 algorithms and results.
The next algorithm we use is stochastic gradient boosting. SGB is same as random forest in that it uses decision trees, adds trees to get better performance, and creates trees with bagging. SGB is different than random forest in that it uses boosting and not bagging. It adds trees to perform better on algorithmic loss function. Trees are grown differently, and trees are added sequentially to minimize loss. The last algorithm we use is k-means clustering. Unlike random forest and SGB, k-means is an unsupervised machine learning algorithm. That means that it trains without labels. The first step is to randomly initialize k cluster centroids, and then assign each data point to cluster with nearest mean and calculate new mean for that cluster. This step is repeated until convergence is met. The confusion matrix on the left displays per class analysis of random forest prediction performance for the multi-class system. Classes with high amounts of training data generally perform better than those with low amounts of training data. This is especially true in random forest, as its bagging will bias the model towards more populated classes. However, some benign classes are being misclassified as DOS Hulk or DOS slow HTTP test despite having the most amount of training data. The confusion matrix on the right displays per class analysis of k-means prediction performance for the multi-class system. K-means did not perform as well as the random forest. This is because k-means is an unsupervised learning algorithm and would generally be outperformed by supervised algorithms on well-structured datasets. This confusion matrix displays per class analysis of SGB for the multi-class system. SGB performed better than both the random forest and k-means. It was able to at least partially classify all of the attack classes, including those with very little data. However, SGB took longer than both the random forest and k-means to train, but its long training time may be reduced by AI techniques such as principal component analysis at some cost to accuracy.
In summary, the best algorithm was stochastic gradient boosting, followed by random forest, and finally k-means clustering.
Our future work includes loading onto a Raspberry Pi on a drone to test the model in a more realistic setting and applying to decentralized drone networks. If you have any questions, then you can email us.